Now let's consider the reflection and transmission amplitudes and the coefficients. The transfer matrix that we have provided, that we have discussed here, that provides an intuitive description of the electron tunneling through the given potential region. Now, if we consider the stationary solution of the Schrodinger equation, if we consider an impinging wave that comes from the left and gets partially reflected and partially transmitted through the potential region. A wave is coming from the left here, one electron is moving in this direction towards the right, it hits the potential barrier, it gets partially reflected and partially transmitted. If we consider that kind of a situation, then comes the question of reflection and transmission. Then we can clearly see that this amplitude Br has to be 0 in that kind of a situation. And if Br equals 0, then the linear equations that we have obtained from the transfer matrix can be written as Ar equals S11 Al plus S12 Bl, while Br being 0, it is 0 equals S21 Al plus S22 Bl. So, we can obtain the reflection and transmission coefficients as we will discuss now. The reflection amplitude, if we call it R, small r, will be given as Bl over Al. Referring back to this picture, Bl is the reflected part and Al is the incoming part. So, Bl over Al gives us the reflection amplitude, which is from the transfer matrix equations here minus S21 over S22. Now, the reflection coefficient which is represented as the capital R and given as R times R star amplitude mod squared equals S21 over S22 mod squared. Now, let us discuss the transmission amplitude. Given as T equals AR over AL. And if we invoke the unimodularity of the transfer matrix, that is the determinant equals 1, we can write the transmission coefficient capital T equals TT star, which is mod of t squared equals 1 over S22 squared. And from this and the unimodularity of the transfer matrix, we can verify that R plus T equals 1. So, in terms of the reflection and transmission amplitudes, we can write the transfer matrix S as 1 over T star minus R star over T star minus R over T and 1 over T. This is the form that the transfer matrix takes for our problem of electrons moving from the left to the right hitting the barrier. So now this transfer matrix has a very clear physical meaning. Next, we will connect the transfer matrix corresponding to a given potential. We will consider a potential Vx, and we will have a transfer matrix S, that is a function of D. Now we will have a connection between them corresponding to a rigid displacement in the potential if we transform the potential from V to Vx to Vx minus D. If we do something like this, then how does the transfer matrix change? The general solution that we have considered earlier, from that we can write this kind of a displacement in the potential, the corresponding transfer matrix SD as S11 S12 e power minus twice I q d, S21 e power twice I q d, and S22. This is the form of the transfer matrix upon this translation of in the potential. When we shift the potential along the x axis by displacement d, the diagonal matrix elements remain unchanged. Only the off diagonal matrix elements, they acquire a phase factor e power plus minus twice I q d.